In this video, we're going to talk about integrating powers of tangent and secant that are multiplied together. This is a little bit trickier than powers of sine and cosine, however, because effectively, except for a negative, the derivatives of sine and cosine really just flip-flop. We go from derivative of cosine is sine, derivative of sine is cosine, and that's simple. But the derivatives involving tangent and secant are a bit more complex. The derivative of tangent is secant squared. Then the derivative of secant squared involves using either a chain rule or a product rule in order to evaluate. It doesn't just flip right back to tangent. The derivative of secant involves secant times tangent, which would definitely need a product rule to go to do again. It doesn't just bring us right back to tangent. So things get a bit more complex. So we're not going to dive quite as deeply into powers of tangent and secant, but we are going to introduce the topic and basically model what we did with sine and cosine. So for the majority of integrals here, we're just going to work with problems that could be worked out by using the Pythagorean identity. And that Pythagorean identity is 1 plus tangent squared equals secant squared. And I know students don't always remember that one. Here's what I do. So I absolutely remember sine squared x plus cosine squared x equals 1. If you take this one and you divide it through by either sine or cosine, you need to do cosine, but what happens is you end up with one of the other two Pythagorean identities that aren't quite as readily used. Sine over cosine gives us tangent. Cosine over cosine is 1. And 1 over cosine is secant. So if you take the original, divide by cosine, you end up with this one right here. It makes it a little bit easier to develop if you just don't remember the positioning of that positive 1. Because in these integrals, that's going to make a big difference. Now, what we would like to do is, in the same fashion with sine and cosine, is preserve a factor for u substitution. So for instance, we might wish to preserve a factor of secant squared, because ultimately what that means is I'm going to use tangent as my substitution so that du is secant squared. Or I need to preserve a factor of secant times tangent to use as du if I am substituting with secant of x. So to help out in identifying when this might work out, if secant has an even power, then you should be able to isolate secant squared and substitute using u equals tangent. If tangent has an odd power, you can generally preserve secant times tangent and then let u equals secant for your substitution. Now, the way I remember this is that, the three basic trig functions that everybody remembers from trigonometry are sine, cosine, and tangent. And in this case, all three of these require an odd power in order to get things to work out. So then just remember the last one, which is secant, has the even power that you're looking for. Now, in a pinch, it's easy to forget even that. So I urge you to just really kind of explore and see when things will work and when they're not going to work. And don't try to force things to work. So I'll show you an example in just a moment that will work one way but not the other, and we can see if we try it the wrong way, what might happen so that we can prevent that mistake. Or at least identify when that mistake is going to occur so that if we are going down that route, we know when to stop and go the other direction. Okay, so in this example here, I have tangent to the 6th of x, secant to the 4th of x dx. So Sine, cosine, tangent, I'm looking for odd powers. I've got an even power tangent, so I don't want to work on that. But I do have an even power of secant, so I want even powers of secant. So I'm going to rewrite this. So secant to the fourth could be written as secant squared x times secant squared x. Okay, which could be written as secant squared x, and it's great to have this rule written down somewhere on your paper so that you don't accidentally put that +1 in the wrong place. I'm changing this secant squared into 1 plus tangent squared, and then I can multiply this with this tangent to the sixth, and I've got a preserved factor of secant, and I can let u be tangent. It's all going to work out just fine. So, for instance, that would look like the integral of tangent to the sixth of x times 1 plus tangent squared x times secant squared x dx, which results in tangent to the sixth x plus tangent to the eighth of x times secant squared x dx. Now, when I substitute, I can let u be the function tangent of x, and du then comes from secant squared x dx. So this part was preserved just for that, for u. So my problem then becomes the integral of u to the sixth plus u to the eighth du, which integrates as, oops, don't need my integral symbol any longer, u to the seventh over 7 plus u to the ninth, pardon me, over 9. And substituting back for u, I would have 1/7 tangent to the seventh of x plus 1/9 tangent to the ninth of x plus c. And then I'm all finished at that point. Now the key things to know that this was going to work, first off, if you remember the rules here about even powers and odd powers to watch out for. But ultimately, I rewrite one of these so that I preserve a factor for du. So when I write secant to the fourth as secant squared times secant squared, then that clues me in. So I have secant squared x, and then times another secant squared x dx. And that clues me in that I can change these remaining factors into tangent, and then the derivative of tangent is secant squared, so this is my du. So that will all work out. If I had tried the other route, then ultimately what I'm going to need is a factor down the road here of tangent x times secant x dx. All right, so secant to the fourth I would be leaving alone, which means I'd have to break down this tangent of x in such a way that, well, actually, I would have written this as secant to the third, because secant to the third times secant x would be my secant to the fourth. So I'm breaking that down. But then I would have also broken down tangent to the sixth as tangent to the fifth x. Now, in this respect, I would be letting u be secant of x, and then my du is, of course, the tangent x secant x dx. Okay? So that means I need all remaining factors outside of this to be secant. The problem is I've got an odd power of tangent remaining. So I could make that tangent times tangent squared, and each factor of tangent squared can be changed into secant, but then I have a leftover tangent that I just can't do anything with. So it's when you're doing that that you run into a situation where it probably tells you that it's not going to work. So in this, I probably should have used a different color, but trying to go this route ultimately will not work for the substitution. And I can't stress enough that if you've chosen the wrong direction, once you realize that, stop, go back to the beginning of the problem, and restart. Because there's only one of two choices. You can't force the integral to work and come up with the correct answer in the end. Like, it's not going to happen that way. Okay, let's go to the next example here. I have secant to the fifth x times tangent x. And what I'm looking for are either odd powers of tangent or even powers of secant. So I have that odd power of tangent here. And because of that, ultimately, what I'm going to attempt to do, so tangent has an odd power, I'm going to isolate secant tangent and let u equal secant for my substitution. So I'm looking to use u equal secant x for my substitution so that du will be secant x tangent x dx. Okay, so let's see what happens when I try that. So if I take one of these factors out of secant, then I would have secant to the fourth x times secant x tangent x dx. All right, so I've preserved this for du. That's great. And then I need to be able to substitute with secant. And I have secant to the fourth. This is fine. There's actually not much I need to do in this problem. So when I substitute, this is going to look like u to the fourth, and then du here will become, or dx, excuse me, all secant x tangent x dx will become my du. So that's what I'm trying to say. That will all be replaced with du, and I therefore have u to the fifth over 5 plus c, or finally 1/5 secant to the fifth of x plus c. Next, I have tangent to the fifth x times secant squared x. Okay, so to work this out, I either need an odd power of tangent or an even power of secant. If you notice, both of those qualify. So I can actually work this problem through either way, and it's going to work out just fine. But that doesn't mean that there's not a best way. Because here's the thing. If I were to preserve secant squared, which is already preserved actually, for du, then I would ultimately be allowing u to be tangent x, because then du is of course that secant squared x dx. I'm practically done and don't have to do anything else, because this would be the integral of u to the fifth du, which is u to the sixth over 6 plus c, or simply 1/6 tangent to the sixth of x plus c. Now, if I chose to go the other direction, then what would happen there is a little bit more difficult. Because you see, the thing is, I would need to preserve a factor of secant x tangent x. So this would be written as tangent to the fourth x, because I'm pulling out one of those to come up with a factor of tangent, times secant of x times secant x tangent x dx. Okay, So this is fine. I have what I'm going to use for du, and then I've only just pulled out factors from these two original terms. Ultimately, because my du is secant x tangent x, I would be substituting with secant, so I need everything else in terms of secant. To get that to happen, I need to change this tangent to the fourth into secants. So tangent, make sure you're careful here, back to this Pythagorean identity up here, tangent squared is secant squared x minus 1. Okay, so I would come back down, pardon the scrolling. This would be secant squared x minus 1 times secant squared x minus 1, because this is effectively tangent squared times tangent squared, which would be tangent to the fourth, times this secant x, times secant x tangent x dx. Now, here's where things get trickier, because I have to distribute and multiply these through, which isn't going to be too bad, but it's certainly not desirable. And then I have to factor this factor of secant back into the resulting trinomial. Then I could use u substitution, and I would arrive at an answer. That answer would look very different from what this response is, but it would be algebraically equivalent. There would be some means of expressing one in terms of the other, at least through the factor, the arbitrary constant c. I'm not going to go through that. I just want you to see that even though you might have more than one way to work the problem, there still might be a best way to work the problem. So if you find that there's more than one way and the way you're going seems to be pretty difficult, possibly look to see what happens if you go the other route, just as an exploration. Next here I have tangent to the fifth x times secant cubed x. Now, in this situation, I have an odd power of tangent and an odd power of secant. So that odd power of secant, I can't do anything to work with that. So I need to work with the odd power of tangent instead. So ultimately, if I'm working with the odd power of tangent, that means I'm going to be substituting with secant. So I'm looking to preserve secant of x, tangent of x factor, in order to do my u substitution. So let's see what happens. So I'm going to take one of the factors of tangent, so this will be tangent to the fourth of x, one of the factors of secant, so that would be secant squared x, leaving me with secant x tangent x dx. All right, now I'm substituting with secant, so I have to write all my factors of tangent in terms of secant. So I'm sort of in the position from the previous problem, if I had gone the wrong direction in the previous problem, that is. But here it's unavoidable. So I do need to take tangent to the fourth, rewrite it as tangent squared times tangent squared, which is secant squared x minus 1 times secant squared x minus 1, and then I have a secant squared outside, and then finally what I'm going to use for du. So secant x tangent x dx. Okay, so let's get moving here. So secant squared times secant squared is secant to the fourth x. Then it would be minus 2 secant squared x, because secant squared times negative 1, and then secant squared times negative 1, those add up to negative 2 secant squared x. 1 times 1 is 1, times secant squared x, and then this would be secant x tangent x dx. If I distribute this secant x, I've got secant to the 6th x minus 2 secant to the 4th x plus secant squared x times this factor. And thankfully, I'm able to substitute here because that's going to make the writing a lot less, because I'm using u to be secant of x. So this will be u to the 6th minus 2u to the 4th plus u squared, and then this is all taken care of by du. Integrating, that becomes u to the 7th over 7 minus 2u to the 5th over 5 plus u to the 3rd over 3 plus c. Or finally, I will end up with, substituting back, 1/7 secant to the 7th of x minus 2/5 secant to the 5th of x plus 1/3 secant to the 3rd of x plus c. And that's my final result there.